think I'll need the mic. Well, I'll do without. And I'm not an amateur astronomer, at least I haven't been in 20 years, but I thought that was an excellent idea to show some of the thinking that we have been doing at our newly established Institute for Data Intensive Astronomy, which is an inter-university initiative spread across 4 universities in South Africa, and of which I'm a research scientist at the University of the Western Cape. So I'll be trying to show you some considerations that we've been doing, about trying to bridge the gap, between citizen science, radio astronomy, artificial intelligence, and to engage, the public of, amateur scientists, citizen scientists as well as amateur astronomers alike. If this is going to sound slightly less coherent than usual, and that's saying a lot for me, this is because we've just opened an exhibition at the museum yesterday, which has got some astronomical backdrop, and hopefully you'll be able to visit while, for those who are visiting while you're in Cape Town, and for those who are in Cape Town, there will be plenty of time, to do that between now and April the 22nd. This is an exhibition about, how we like to put it, the relationship between humans, the environment, the sky, and astronomy. And it's been realized in collaboration with a number of partners, locally, mostly the National Research Foundation as part of the History of Astronomy Roadmap. But I'll get to that at the very end. So, some of our assumptions, as data scientists, as radio astronomers, are that citizen science, on one hand, is not real amateur astronomy because, at least my current understanding, previous understanding of citizen science, had to do with running some processes to detect extraterrestrial intelligence on your laptop or classifying, some sources, from a web browser, and this didn't really seem like getting dirty, with the instrument and the data reduction, so it didn't seem to qualify, like real amateur astronomy. On the other hand, radio astronomy is not only, technologically somewhat more complicated than optical astronomy or infrared astronomy, but it's not as visually compelling, and this is, a very widely held assumption that I would try to dispel. And last but not the least, of course, artificial intelligence has been talked about, before I was born, probably, and but the general understanding is that that is also not for amateurs. And we'll get to analyze some of these assumptions one by one in the process. Well, starting from citizen science, apparently in its technical definition, it goes back, a long time. Apparently, Henry David Thoreau, was considered a citizen scientist in his days. But at any rate, it only made it into the Oxford English Dictionary in 2014, and it's now defined, as you can see, with scientific work undertaken by members of the general public under the direction of professional scientists and scientific institutions, or at least in collaboration with them. So this is not a new idea, but it's certainly being reborn, with the easy availability of digital detectors and small cost, small form factor telescopes and so on and so forth. So this also infringes on the definition of what is a scientist, why, and what people are doing science. So it's a very interesting question, it's a very interesting definition. And of course, a lot of people, particularly those more inclined, for computer science, were exposed, to some sort of passive citizen science. For instance, the search of extraterrestrial intelligence through unused cycles on your laptop when you were at the university, versus, the more active sort of citizen science. Now, the recent developments of citizen science have been very rapid, as I will show later, and they have basically been driven, not only by the wide availability of computers, crucially through internet connections, but also by the need by professional astronomers of inspecting and classifying in some fashion very large data sets, that have been gradually becoming available over the past 20 years that have now surpassed even our wildest imaginations. And here I only show one 15-year-old survey project in the optical, such as the SDSS, and one upcoming survey project to be carried out in the radio with Meerkat in the Karoo. So one of the things, I mean, that astronomers picked up very quickly, I mean, when this new craze of citizen scientists, I mean, came along over the internet, was defining a project that was visually compelling and that appealed, I mean, to the everlasting fascination of people, I mean, with astronomy, with objects in the sky. And that was called Galaxy Zoot. I mean, the general idea was that citizen astronomers would classify objects, I mean, based on their appearance, based on their color, and so on and so forth. And even a very basic classification, I mean, between early and late type galaxies and intermediate, and between blue, green, and red galaxies, I mean, managed, I mean, to provide some very useful results. I mean, at a time, I mean, where automated processes, I mean, to take care of such problems, I mean, were not really available, I mean, as part of the general toolbox of astronomy. And largely, I mean, through the trust of Galaxy Zoot, I mean, the Zooniverse came about with this slogan of people power research. So it stretches, I mean, from anything from animal detection, I mean, to inspecting, I mean, trends, I mean, in weather patterns, and so on and so forth. Now, the interesting thing is that this, at first, I mean, seemed to probe, I mean, internet connectivity. It's now, and even though, I mean, this has now spread considerably across the world, I mean, the bulk of citizen scientists, I mean, defined as those who participate, I mean, within Zooniverse projects, I mean, still seem to to cluster in Europe and in the US, I mean, with some stretches, I mean, over the somewhat more populated regions elsewhere. The distribution of ages of people doing that is apparently relatively flat. If you ask me, I mean, there's plenty of people doing that from the office. I mean, I would have thought that 30 to 35 was when people, I mean, couldn't really take time off to do this sort of things, but apparently, I mean, plenty are. And so what they think about their participation, how they view their own participation, unsurprisingly, I mean, with close to 90% of their votes, I mean, they seem to want to contribute to scientific progress, and they're more generally fascinated, I mean, by the projects they contribute to. So they actually like, I mean, probably looking at the images and carrying out these rather boring tasks, I mean, in any other context. Of course, the reason why we want to do that is because, I mean, as scientists, particularly, I mean, the more established ones, I mean, they've got very strong constraints on their time, and if you want to be able to spot penguins in an image, I mean, it's much more effective to get thousands of people who love penguins to do that for you, so that you can actually pinpoint, I mean, a migration of penguins with the help of some citizen scientists. Okay, this is all very well, and when it came time for radio astronomers to consider making use of citizen scientists to solve some of their problems, I mean, they started trying to overcome, I mean, the feeling that radio astronomy was a rather exotic discipline. I mean, these are some of the brightest radio objects in the sky. Very often, I mean, when they were first discovered and classified by Bernie Fanaroff and Julia Riley, they weren't detected in the optical. And some of the most dramatic objects have been since, I mean, analyzed in excruciating detail, including one of the first, what used to be called radio stars, and what eventually became to be known as Cygnus A, and which is actually a radio galaxy. I mean, the thing is that moving from these very fluffy images in the radio, I mean, to the actual backdrop of a very rich optical sky, I mean, has required, I mean, probably 30 years of technological progress. So radio astronomy, I mean, probably got a bad name at first, and the difficulty in improving the technology behind radio astronomy, I mean, has meant that, I mean, it has kept, I mean, this bad name, I mean, for the past 40 years, probably. So what I want to show now is that by combining radio astronomy with optical and infrared and X-ray astronomy, I mean, you can determine an awful lot of more information and engage, the public somewhat better, than just by relying on optical and radio separately. So this is the center of what is, I think, Saint-Gervais, and this is the optical belly. This is an image of 10 second, and the kind of things that one can do, with adaptive optics over with very high resolution, at the very center is extremely interesting, but it only covers a fraction of the actual extension of the source in the radio. Through different radio observations, you can see that the source actually stretches much farther, and again, through improved radio imaging, you can get to the actual full extension of the source in the sky. So this means that the combination of optical and radio is really integral. To trying to understand the full physical processes underlying this, but it also provides an extremely interesting visual appearance. This rivals some of your deep sky objects. If you ask me, so it's something that is worth keeping in mind. Even more interesting is to take a look at the wide variety of shapes of radio sources. These are radio contours, on top of infrared images, I think. So radio sources come in all shapes and sizes, and the actual classification of their shapes and their sizes, is a job that has kept, generations of astronomers busy, for years. And the interesting thing is that this is not only a problem that was apparent in astronomy. This is a problem that has been around forever. How you recognize shapes and sizes in an image, and of course, in Africa, we have a number of things that we might want to do. In order to monitor wildlife. This is an illustration of Julie Banfield's fascination. With African wildlife, but more importantly, the kind of problems that we face with image recognition, are exceedingly similar, to what the people working with machine learning and artificial intelligence are facing at the moment, and that's why, when we developed this program called, this extension of Galaxy Zoot called Radio Galaxy Zoot, we also relied a lot on the combination between citizen science and artificial intelligence to solve the problems. So the basic definition of Radio Galaxy Zoot is comparing the radio image from the VLA to the infrared image from the WISE satellite in order to identify the host of the radio source. Radio sources can extend much wider than the infrared position. As you can see here, the radio contours, which you can see on the left-hand side, stretch much more than the individual extension of any infrared source. So Radio Galaxy Zoot allows you to take a look at the radio contours and the infrared image by using a slider, and to comment upon whether you find different lobes of radio emission, and whether you can pinpoint a central position, a central infrared position associated with the radio source. In this case, you should see an infrared source at the center of the radio image. Unfortunately, the contrast is not good enough for you to see that. Perhaps more interestingly is that you can create a discussion. There's basically a little online forum, for each and every object, and of course, whereas the vast majority of objects are relatively trivial and get classified relatively quickly by users, there are a lot of outliers, that actually baffle, most experienced users, and these are the ones which actually are the most interesting for scientists. In another illustration of Julie's fascination with the African landscape, she tries to compare the appearance of a blank environment, such as in this case, which may be, for instance, the infrared non-detection of a radio source, with a very prominent, appearance of an object, sitting right there. Only you would never see it, unless you take a look at both images. And this is the illustration of what objects can look like. When things are simple, but let's, okay, this isn't working. Okay, well, I'll show you later. One very important point that we should bear in mind is that whereas some of the Zooniverse projects have attracted, I mean, somewhat some sort of attention, I mean, outside of the main core of, well, English-speaking countries, I mean, and in this case, Russian-speaking countries, which is interesting, if you ask me. The Radio Galaxy Zoot project specifically, I mean, was really only popular, I mean, within some very limited language areas and crucially geographical areas. So one, of course, I mean, internet connectivity is nowhere as good as elsewhere, well, and pervasive and cheap as elsewhere. But we should certainly, I mean, interrogate ourselves whether there is anything that we can do, I mean, in order to create apps that are friendlier, I mean, for users here. The end result of, well, the end scientific result of the project, I mean, can be shown here. I mean, there have been 2 million classifications, I mean, by different citizen scientists and 11,000, I mean, registered scientists, although, I mean, the vast majority of the classifications were carried out by some 1,000, 2,000 tops. The interim data release will have 74 radio sources that have then been classified many times in a coherent manner by different users, and they will be classified, I mean, in a number of ways, I mean, by astronomers. Some of the most interesting, I mean, gold nuggets, I mean, sitting at, well, at the bottom, I mean, of this process, I can only show one, and this was a somewhat diffuse radio object, I mean, on top of the infrared image that was identified by a couple of users, I mean, at about the same time in 2013. And, well, it was only published a couple of years later after, I mean, going through first a discussion online. I mean, this is the comparison of two radio images that are showing slightly different resolution and slightly different diffuse emission of the source. And so this indicated, I mean, that the source was an interesting one, and specifically, I mean, a galaxy cluster. It was then possible, I mean, to relate this, I mean, with online resources. This is, for instance, the NASA IPAC Extragalactic Database, which was probed in order to take a look at the optical image. And by following this discussion, I mean, astronomers were eventually able to determine, I mean, the actual physical nature of this source, I mean, by a discussion carried out on online forum. And this is, well, the illustration of the actual source. I mean, so the original image, I mean, was not particularly telling at the top right, but the final image, I mean, with better radio data, I mean, actually tells a somewhat a rather different story. And this was, well, published, I mean, between other things, I mean, as part of the Radio Galaxy Zoot science plan, I mean, including, I mean, the two citizen scientists who contributed to that. I'm not sure how I'm doing for time, Tim. Excellent. No, I mean, I got 10 or so. Okay, great, because I thought that I started a little earlier. So the last aspect I want to bring up is that while this is all very well, I mean, I think there's a lot of scope, I mean, for improving the exposure that particularly pupils in South Africa have to such tools, I mean, in order to develop, I mean, better understanding and fascination, I mean, with science and astronomy in particular. There are some challenges, I mean, that are upcoming. I mean, one is, of course, the challenges of the deluge of data, I mean, that are coming from future facilities. I mean, we don't really need to go into the details, but the general idea is that exponential increase in the kind of data, I mean, you're looking at, I mean, doesn't scale very well, I mean, with the kind of improvements that we have in connectivity and in data storage, I mean, at the individual level. So an illustration of this problem is what LSST will produce. I mean, still I mentioned the mission, the telescope that is being built, I mean, on the Chilean mountaintops. The telescope will create opportunities for detecting up to 1 million transient events per night, and the alerts will be available within 60 seconds. So I'm not sure how many amateur astronomers are sitting out there, I mean, but you're probably not going to be able to inspect 1 million transients per night. So you really want a way to be able to tell, I mean, what are the most interesting ones, and this is in most respects a classification problem. How do you classify 1 million variable sources per night. I mean, in an homogeneous fashion and in a rapid fashion, so that amateur astronomers as well as professional astronomers can try and follow up the most interesting ones. So this is where artificial intelligence and machine learning comes into play. I mean, it was a moniker, I mean, that has been around, I mean, for at least 40 years. I mean, it only became practical recently, A, because of the larger availability of data in digital format, and B, because, I mean, computation and software tools, I mean, have caught up, I mean, with the needs, I mean, of greedy artificial intelligence software. Now, of course, there's a couple of competing visions, I mean, of artificial intelligence or machine learning in the community. I mean, one is, of course, that machine learning is going to solve all of our mundane problems. The other one is that, robots will eventually rebel and kill us. I think this is worth bearing in mind, I mean, particularly because it's one of the debate, I mean, that will inform a lot of the science policy and the understanding of science. I think should remember that physics and astronomy, I mean, didn't really have a good name, I mean, after the Second World War because of the association, I mean, with the nuclear bomb development and the like. And starting perhaps from the space race, I mean, in the US, I mean, there has been a lot of work in trying to improve the public image, and astronomers now are doing, I mean, extremely well, I suppose, in the public eye. But I mean, this is a challenge that we also need facing, and we probably want to engage, I mean, the public in order to understand the implications of the developments in machine learning and artificial intelligence. Now, in astronomy and through citizen scientists, we have the opportunity to bring together the wisdom of the crowd, I mean, by getting lots of individual users to label observations taken by astronomers or taken by their own personal observatories, create a training set that then can be used by the machine learner, so the code that actually learns the properties of the training set, and then can be applied to the test set in order to create a model that predicts the classification of data that has not been seen as yet. So classic example is 1 million LSST transients. I mean, will be difficult to classify overnight, but they will generally look, well, by and large, they will look the same over the 10 years of LSST. So if you get 1 million transients in a citizen science project database, you can then looking at them, and over the first 6 months of the mission, I mean, you can classify them, and you can provide machine learning algorithms the opportunity to then classify them during the course of the night, I mean, in real time. And the reason why I think this is particularly interesting for South Africa is that this kind of technology, I mean, is now running on off-the-shelf artificial intelligence software, I mean, that can be run, I mean, by a high school kid, I mean, that is fluent in programming and offers the opportunities to engage youngsters in a way that is perhaps, I mean, different, I mean, from the kind of engagement that conventional amateur astronomy offers, but that is rather important nonetheless. And the IAU OAD here, I mean, has got together a first version of their data science toolkit, which is an excellent example of resources that are becoming available and that can be tuned, I mean, to the somewhat younger, I mean, generation, I mean, that is keen to learn, I mean, by doing some coding, possibly in the cloud straight away, I mean, without needing to access, I mean, any personal laptop or personal desktop at home. And of course, I mean, this doesn't goes without saying that this is important in trying to create, I mean, a workforce that is, I mean, ready for the needs of future employers. And I mean, this is particularly important in the South African context, of course. So I have a couple of things that I would like to hear your thoughts about. And that is basically how can astronomy, I mean, keep being one of the people's, I mean, favorite, most engaging sciences. I mean, again, thanks to its imagery. I mean, even in a position, I mean, where different sciences, I mean, are carrying out, I mean, surprising advances. And I claim, I mean, I believe that the combination of citizen science, radio astronomy, and artificial intelligence can be, I mean, an interesting avenue, I mean, to engage a somewhat more diverse or a somewhat different audience, I mean, than the one that is currently being engaged by astronomy in general. And of course, I mean, how can we better engage the public? I mean, by creating better tools, I mean, to get, well, better tools for them, and making sure that they know about them and that they can use them, I mean, even in the context of a somewhat limited connectivity, such as is the case in Africa in particular. And I will leave you with our Cape Times article today about our exhibition. Tomorrow at the planetarium, I'm told that there might be an opportunity to visit the exhibition before the planetarium show, if you're going to that. Otherwise, I mean, the exhibition will be open between 10 o'clock and 5 p.m. Every day, I mean, between now and April the 22nd. So please come and have a look at the exhibition while you are here.
Thank you, Mattia. Questions? No questions? Thank you.
So do you have updates on LSST's public outreach program?
No, I mean, well, South Africa is only loosely involved. I know there's a couple of people in Tucson working on it, but and I know that LSST is sponsoring a large, a rather strong program of data science schools and the like. So I would imagine that they will be working on bringing, I mean, together, I mean, the needs of data science, I mean, and the need to reach out to students and the like, but I don't have a good handle on what the actual program is. I'm this side of the pond. So either of you.
Were you able to measure the accuracy increase in the various participants as they participated?
Actually, this is a classic data science problem. I mean, we were, and there are also some interesting indications that different languages, I mean, or at least different geographical areas work differently, and that can only be attributed for in a small portion to the education level of the respondents. We try and factor that out. But there's extensive work in that, and it's one of the most interesting bit of applied data science, I mean, for the citizen science things.
Converse question. Can you qualify how all the classifiers working Olympian sports experts, citizen scientists say the answers?
Mm-hmm. Well, I mean, there's again, I mean, every problem is subtly different, but there are conventional ways in which statisticians do that, and statisticians compare the blind performance of astronomers, for instance, with the blind performance of amateurs, and they try and create problems that where this performance reaches, I mean, effectively plateaus after a learning curve that is relatively rapid. So there are problems that where effectively, I mean, amateurs, I mean, don't perform anywhere as well as astronomers, and that is a worry. There are also problems in which astronomers don't astronomers overperform any machine learning algorithm that we currently know of, and that's probably, I mean, because they have access, I mean, to a wide baggage of previous information. So it is an open problem, and it's one of the things, I mean, that is keeping people busy, particularly with the idea of using the SKA to do transient detection. So SKA will be a transient machine, not unlike LSST. I didn't put it up because it's not as well defined as LSST. So it's difficult to tell how much of the 1 exabyte of data that the SKA could produce on any given day, I mean, we may want to retain for people to inspect. And I mean, we're not going to get that many people. So we really need to develop ways to understand how many classifications we need from citizen scientists in order to be able to answer a certain problem to a 1% level of accuracy, for instance. If we can get a 1% level of accuracy on the classification between 2 different classes of objects, this is already, well, this is an objective that we can actually work toward and that we can plan for.
Time for one more.
Was there a recognition system or reward system built into your operation such that people could learn where they made their mistakes, improve upon themselves, and then somehow become recognized in the community for their efforts?
Was it two questions actually? I mean, was it one about the possibility of being corrected and one about the possibility of being recognized? I mean, for their efforts. There are of course rankings. I mean, that try to encourage people. I mean, to do better. I don't think the results of your classification can be told to you before the end of the project, because that would invalidate, I mean, the sort of statistical analysis you're doing. So we're not really telling the user whether it's getting things wrong, partly because we don't have an answer a priori. I think there hasn't been any investigation about what happens if, there must have been in some specific journal, I mean, but I'm not aware of any study of what happens, I mean, if you actually help the citizen scientists to learn during the process. This is more a question for e-learning, I mean, such as the kind of things that you might want to do specialized learning for kids at school, and it somehow falls outside our area of interest, but it's an excellent question.
Thanks very much, Mattia.
Thank you.